When randomness turned out to be an illusion, for a long time, randomness felt like the absence of rules. Events happened without reason, pattern, or warning, or so it seemed. To understand why randomness itself came under suspicion, we have to revisit how uncertainty was once understood. When outcomes could not be predicted, they were labeled random and left unexplained. Dice rolls, coin flips, and noise and data were treated as nature's way of hiding its intentions. This mattered because randomness shaped trust. It defined risk. It justified uncertainty in science, economics, and everyday life. If events were truly random, then no deeper explanation was possible. Chance was the final answer. But as measurements improved, cracks began to appear. Patterns emerged where none were expected. Repeated experiments produced distributions that were too stable to be accidental. The noise began to look structured. At first, this structure was dismissed as coincidence. The datasets were small. The tools were limited. But with time, patterns refused to disappear. Randomness began to look less like chaos and more like ignorance. The turning point came when simple systems, governed by clear rules, produced outputs indistinguishable from random noise. The implication was unsettling. What looked like chance might be determinism in disguise. If that was true, then randomness was not a property of the universe. It was a property of our understanding. As researchers probed deeper, they found that many so-called random processes were driven by hidden variables. Tiny influences, too small or too fast to measure, accumulated into outcomes that appeared unpredictable. The rules existed. They were simply out of reach. This insight blurred the boundary between chaos and chance. Systems followed strict laws, yet behaved erratically because sensitivity amplified microscopic differences. What looked random was often deterministic complexity, unfolding beyond our ability to track it. The discovery reshaped statistics and probability. Models no longer assumed pure chance by default. They accounted for structure, bias, and dependence. Noise became something to analyze, not ignore, and prediction quietly improved. This mattered because decisions relied on assumptions about randomness. Risk models, security systems, and simulations all depended on whether events were truly unpredictable. If randomness was an illusion, then better understanding could mean better control. But control came with a cost. When systems were assumed random, responsibility could be shared with chance. Once patterns emerged, accountability returned. Failures could no longer be blamed on luck alone. The tension grew as models became more powerful. Predictions sharpened, surprises shrank. Yet uncertainty never vanished completely. Something always escaped measurement. Randomness was losing its mystery, but not its usefulness. It was becoming a boundary, not an explanation. The conflict intensified when attempts to eliminate randomness began failing in unexpected ways. Even when hidden variables were identified, new layers of unpredictability emerged. The closer researchers thought they were in full control, the more complexity revealed itself. This led to a paradox. Deterministic systems could generate behavior more unpredictable than true randomness. Patterns existed, but they were buried beneath layers of interaction. Understanding the rules did not guarantee mastery of the outcomes. In technology, this meant systems behaved differently under scale. Algorithms worked in isolation, then failed in networks. In finance, models assumed independence, only to collapse when correlations suddenly aligned. The illusion of randomness hid deeper connections. The emotional core of the conflict was humility. Mathematics was revealing that unpredictability did not always come from ignorance alone. Some systems were fundamentally resistant to long-term prediction, even when their rules were known. This forced a shift in mindset. Instead of trying to remove randomness, researchers focused on managing uncertainty. Robust systems replaced optimal ones. Flexibility replaced precision. Randomness had not disappeared. It had changed meaning. And understanding that meaning became essential for survival in complex systems. The resolution emerged when randomness was no longer treated as an enemy. It became a signal, a sign that a system was too complex, too sensitive, or too interconnected to be controlled in detail. Instead of fighting it, mathematics learned to work alongside it. This change transformed how systems were built. Engineers stopped chasing perfect prediction and focused on stability under uncertainty. Economists replaced single forecasts with ranges and scenarios. Scientists accepted that some outcomes could only be described statistically, not precisely. What mattered was not eliminating surprise, but surviving it. Systems designed with uncertainty in mind bent instead of breaking. Redundancy replaced fragility. Adaptation replaced precision. The illusion of total control was abandoned. Randomness, once feared as ignorance, became a guide. It showed where models ended and reality began. It revealed limits before collapse. In many cases, it provided early warnings that rigid systems could not. In the end, randomness was never the opposite of order. It was a shadow cast by complexity, a reminder that knowing the rules does not mean owning the future. Today, the most powerful insight is not how to predict everything. It is how to prepare for what cannot be predicted. So, what do you think? Are we repeating the same mistake again?